Okay, we're talking about waves. This is the review for the material covered after quiz 6. So we have some displacement, and we want to look at the displacement produced by the wave as a function of distance or as a function of time. Now, if I make a snapshot, so this is a snapshot, maybe it's at, for example, t equals to 0, then I have this behavior as a function of x, and the distance between 2 points that are repetitions of each other is the wavelength lambda. If instead I look at some particular value of x, for example, x is equal to 0, and figure out what displacement we get as a function of time, then I get this pattern, again another sine wave, but the period of time between repeating points is called the period, capital T. Okay, so now we can talk about the speed of the wave. We're talking about traveling waves. The speed of the wave, v, is equal to the wavelength lambda times the frequency. Now, we also know that the frequency is 1 over the period. So we can write, therefore, that the wave speed is also the wavelength over the period. Okay. Now, we can also define this angular wave number. So it's written as small k. That's not the spring constant. So if there's no spring in the problem, k stands for wave number. And that's 2 pi divided by the wavelength. This is analogous to the angular frequency omega, which is 2 pi divided by the period t. Okay. So some other formulas that hopefully you're aware of is that the angular frequency is 2 pi times the frequency. Now I can also write the wave speed, v, as the angular frequency omega divided by the wave number, k. So now let's consider a traveling wave. We have this wave here, and then at some later time it's moved forward, let's say in the positive x direction. Then I can write the displacement. So I've written this as y, but typically I should have written it as d. Okay, I'm used to writing it as y, and that's how I wrote in this review, but you can write this as d is equal to a sine of 2 pi over lambda x minus 2 pi over capital T t. Okay. Another way of writing it is d is equal to the amplitude a times, and I can pull out the factor of 2 pi over lambda, and then write it as x minus v t. And the third way of writing it is a times the sine of kx minus omega t. So k is the wave number, and omega is the angular frequency. So these three ways are equivalent ways of writing this traveling wave moving in the plus x direction with wavelength lambda, with period t, and as a result, wave speed v. Let's go on. If the wave is moving in the negative x direction, then where we had the minus signs, we get plus signs. Plus here, plus there, plus here. A sine of 2 pi over lambda x plus 2 pi over t, capital T, I'll fix that. T, and a 2 pi over lambda x plus vt, and a sine of kx plus omega t. Okay, for a transverse wave, the displacement is perpendicular to the wave motion. But for a longitudinal wave, the displacement is parallel to the direction of wave motion. Okay, so what I've drawn here are what appears to be transverse waves, but we can have longitudinal waves that are oscillating in directions parallel and anti-parallel to the direction of motion. Now, if we have a string with a tension Ft, and let's say the length is L, and the mass of the string is m, then we can define the mass per unit length mu as m over L. And so now if we have vibrations or transverse waves on a string, the wave speed will be v is equal to the square root of the tension Ft over the mass per unit length mu. Now if we add two traveling waves together with the same amplitude, same wavelength, and same frequency, but they're going in opposite directions, we end up getting what's called a standing wave. Instead of something moving, these lobes just flip up, vibrate up and down. In the standing wave, we have something called a node, where the displacement is 0, and then we have an antinode where the displacement reaches maxima and minima. Okay? So notice where the string doesn't move, antinode is where the string moves the most. Now we can talk about the modes of the string, vibrating string. So if I have a string of length L, we set the wave speed v is equal to square root of the tension over mu, the mass per unit length. The longest possible wavelength is when I have half a wavelength, this sort of football-shaped object is filling the whole length of the string. This is what's called n equals to 1, or the fundamental mode, or the first harmonic, n equals 1. And lambda 1 is equal to, the wavelength is equal to 2 times L. And the frequency f1 is v over lambda 1. This is a general formula. The frequency is wave speed divided by wavelength, and that's v over 2L. If I go to the next harmonic, I get two of these half wavelengths, so two of these footballs, n equals to 2, and that's lambda 2 is equal to 2L divided by 2, or lambda 2 is equal to L. And the frequency f2 is v over lambda 2, and that's v over L. So in general, the formula for n equals 1, 2, 3 is that the wavelength lambda sub n for the nth harmonic is equal to 2L over n. So for n equals 1, it was 2L. For n equals to 2, the second harmonic, it's L, and so on. And the frequency Fn is the wave speed divided by lambda n. And so plugging in this formula, we get nv over 2L. Now, sound is a longitudinal wave which the ear can hear. In air, the speed of sound is about 340 meters per second. In a particular problem, they will probably give you the exact value they want you to use, because it depends on temperature. Now, if I have a pipe that's open on two ends, like shown here, the lowest harmonic, n equals 1, has these antinodes at the two ends. You have antinodes for the open pipe ends, and lambda 1 is equal to 2L, and f1 is equal to v over lambda 1, which is v over 2L. It's the same formula as for a string. This is the fundamental mode of the first harmonic. If we go to the second harmonic, we have, again, antinodes at the two ends of the open pipe, a pipe that's open on both ends. This is n equals to 2, lambda 2 is equal to L, and the frequency f2 is v over lambda 2, so that's v over L. So in general, n is equal to 1, 2, 3. We have the same formulas for a string. Lambda n is 2L over n. Fn is v over lambda n, which is nv over 2L. Now, if we have an open-closed pipe, one that's open on one end and closed on the other, then the situation is a little different, because we have an antinode at the open end and a node at the closed end. And so we have n equals 1 here as the lowest mode, and lambda 1 is equal to 4L. F1 is equal to v over lambda 1, v is equal to 4L. That's the fundamental first harmonic. Now, there's no even harmonics. There are only odd harmonics. Okay, and so we have n equals to 3, and this corresponds with this sort of shape where we have an antinode here and a node there. N equals to 3, lambda 3 is equal to 4L over 3, and F3 is equal to v over lambda 3, or 3v over 4L, for the third harmonic. In general, we only have odd harmonics for the open-closed pipe, 1, 3, 5, 7, 9, so on. And the formula from the wavelength is lambda n is 4L over n, and the formula for the frequency, Fn, is v over lambda n, or nv over 4L. If you have any questions about this, please ask the student who's supervising today's lecture. Okay, now let's review interference. So let's suppose I have two waves that are essentially doing the same thing, a sine of kx. a sine of kx. When I add them together, I get twice a sine of kx. That's called constructive interference, when they add together and make a bigger signal. We can also have a phase change, a phase shift of pi, a phase change here, putting the extra pi radians here. But adding pi inside of the sine function is actually the same as flipping the sign overall of the sine function. And so when I add these two together, you notice that they'll just cancel out to 0. And this is the example of destructive interference, completely destructive interference. So now if I have 2 point sources of sound which are starting off in phase with each other, and then I'm an observer here with distance d1 and distance d2 from the two sources, I can talk about whether I have constructive or destructive interference. If the difference in length between the two d1 and the d2 is an integer number of wavelengths, then the signal from S1 and S2 are coming together. They're oscillating together, and we are in phase, or we have constructive interference if the difference in length is an integer multiple of lambda, the wavelength. So n equals 0, 1, 2, 3, and so on. Now, we have destructive interference, so if the difference in the distances d1 minus d2 is in between the integers. In other words, half integers, n plus 1/2 lambda, where n equals 0, 1, 2, and so on. And that's when they cancel out. The last topic, or well, the second to last topic is the Doppler effect. So we have a source that's producing some sound, and the velocity of the speed of sound will be written as v, so v will be speed of sound. That's on the next page, but I'll just write that here, and I have some observer. The velocity of the source is vs, the velocity of the observer is vo, and the convention is that if you're going towards, you're positive. If you go towards the other, you're positive. So vs is greater than 0 if the source is moving towards the observer. Okay? But it's negative if it's moving away from the observer. The same thing for the observer. The velocity of the observer is positive if it moves towards the source, and the velocity of the observer is negative if it moves away from the source. So in both cases, it's positive if it moves towards the other, and negative if it moves away from the other. Okay, so then the formula is that if v is the speed of sound, and f is the frequency of sound emitted by the source, then the frequency f prime heard by the observer, f prime is equal to f times v plus vo divided by v minus vs, using the sign conventions I've just mentioned. When they're moving towards the other object, they're positive. The very last topic is beats. When two frequencies f1 and f2 are close in value, then one can hear this wah, 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 wah sort of a sound, these beats. Okay, where there's this envelope that has a certain frequency to it, and the beat frequency is the absolute value of f1 minus f2. So f1 and f2 are frequencies, you just take the difference, and that's the frequency of the beats. If you have any questions, please ask the supervisor in today's lecture.